Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by AIST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
And also, can both of you turn on the camera? Okay.
Okay.
Okay. Hi everyone. Welcome to this computational fabrication seminar. Today we have 2 speakers, Nobuyuki Umetani and Yuki Koyama, to share their research on interactive user-driven computational design. We will have a short Q&A section at the end of the talks. If you have any question, please post it in the YouTube live chat box on the right of the screen. Our motivational talk is given by Professor Nobuyuki Umetani. Nobuyuki Umetani is an associate professor at the University of Tokyo. Previously, he was a research scientist at Autodesk Research, leading the design and fabrication group. He was a postdoctoral researcher at Autodesk Research and Disney Research Zurich. He received his PhD degree in 2012 from the University of Tokyo under the supervision of Takeo Igarashi. He is broadly interested in physics simulation, especially the finite element method applied for computer animation, biomechanics, and mechanical engineering. So, Professor Nobuyuki, now the floor is yours.
Okay. Thank you very much. Thank you very much for introduction. Song, just one favor. Could you turn on the screen sharing?
Oh yeah, sorry.
Yes, permission for the screen sharing.
Okay, now it should be okay now.
Okay. Yes. Perfect. Thank you very much. Okay. Can you see the screen?
Yes.
Okay, thank you again for fabulous introduction. So, hi, I'm very pleased to give this talk, and I'm really honored to invited such a seminar for this fabrication, computational fabrication. My name is Nobuyuki Umetani, and today's motivational talk is titled as Design Exploration with Interactive Simulation. So let me give a short introduction before the talk. As I'm an associate professor at the University of Tokyo, and I'm interested in the cross section of the mechanical engineering and computer science. And that is knowledge of making and computational method and interactive technique. And so in a nutshell, I'm seeking some good interface and methodology for personal fabrication. So recently, the computational fabrication device was widely available to public. So before the fabrication machines such as lathes and hard, metalling workshop is only available for professional. But thanks to the innovation of the additive manufacturing, such kind of automotive fabrication device was easily available to public, and we can enjoy fabrication at the home. But in terms of software, it's still under development. As far as I know, the software to make something is still difficult to use for for many people who don't have expert knowledge in the making. So I'm interested in developing some software, and computational fabrication software for ordinary people, non-expert people, it should be designed specially because different from professional designer. These people who make something is not paid, but they are willing to make something because it's enjoyable. So we have in the software design, we have to take care of the design to create what makes this process of design enjoyable. And in my thought, it's this is essentially will be important in two aspects. So one is originality in the design, more than the optimal spec. So modern engineering software can maybe design automatically some with respect to optimizing spec. But that does not mean it's making something original. So you have to facilitate the making some originality of the user. And also similarly, the software should be not automatic, like just pressing button and the design just come out, because we have to interact and explore the design, and while do so, we have to some kind of emotional attachment to the object we design. So this aspect means that the software need to have interaction that allow many trial and errors. And what I'm interested in is not just design of geometry, but functional design. That is such as like instrument that have a right tone, or clothing that fit to the body of the person, and furniture that doesn't collapse. And these designs are not trivial because the performance of this object geometry is not directly infer from the geometry, and we need to some simulation, some kind of simulation to validate the design. But typically in the professional software, the design and simulation are totally separated, and we have to bring design into simulation is too much effort and taking too much time. And it's very difficult to understand the simulation result to feedback to the design. So my approach is tightly connect design and simulation. So simulation happen while design, and human is creating during the simulation to tightly integrate it into design space to facilitate the original design for the functional shapes. So I did many researches, studies for various functional objects such as furniture or musical instrument or clothing or sometimes airplane and kite. But today I give some example, two examples of a fashion design. So in the fashion design, the clothing we wear is made out from the pattern, two-dimensional pattern. But after it is cutted and sew it together, it's have some three-dimensional form. But having some 3D geometry and designing two-dimensional pattern to fit the three-dimensional body is very difficult because the dimension is different. So I made some interactive demo to make this process very easy for novice people. Let me show you a demo. Okay. Okay, in this demo, there is a closing simulation, and closing simulation try to put the closing on the top of this this creature. But typically, the closing simulation and the design of pattern is separated. So if I change the closing pattern, I need to run the simulation from scratch. But in our simulation, we developed some method to tightly couple the design and simulation. So here, I change the closing pattern. It's immediately feedback reflected to the design of the closing. And this drastically makes the pattern of the design of the pattern easy, because we know the simulation result immediately. Okay, let's go back to the result. So in this research, the interactive feedback is essential, and here to achieve this interactive speed, I use the idea of sensitivity analysis. So we can think the static closing deformation as a function of mouse that's change the closing pattern in 2D space. But this function is very difficult to evaluate. It takes time. So instead of evaluating this function, I compute the sensitivity that is a differentiation of the static closing position with respect to mouse. And with this sensitivity information, we can quickly feedback, like gives a linear approximation to the user, so that the simulation doesn't stop or doesn't freeze and continuously gives users the feedback. And we can print out the pattern and for the larger pattern, and we can get this kind of wearable result. Okay, the next example is a computational musical instrument design that is a metal phone. A metal phone is usually rectangular, and this is not, this is super boring, and it's not originality is not there. So we want to design arbitrary shaped metal phone. And in this software design, the user can change the two-dimensional shape of the metal phone while looking at the eigenmode, like how it's vibrate, how this metal piece vibrate in real time, and we can see the the musical note on the fly, so that the user can edit the shape while looking at the target, looking at the metal piece frequency of vibration. So that's it have a right vibration frequency. And here is the final result of the metal phone. So it's a fish-shaped metal phone designed by some artist, and it's very difficult to create, because each piece of the metal plate should have some represent entire fish shape, while it's have to vibrate in a certain frequency. But computational interactive computational design can achieve this kind of very difficult design. So let me conclude my talk. So we do some I'm interested in personal fabrication research, and this is kind of interdisciplinary area that's involved in mechanical engineering, numerical method, and interactive technique. And yeah, we can make some very unique original things out of this line of research. Thank you very much.
Thank you, Nobuyuki, for the inspiring talk. So our deep dive talk will be given by Dr. Yuki Koyama. So Dr. Yuki Koyama is a researcher at the National Institute of Advanced Industrial Science and Technology, where he is a member of Media Interaction Group. He received his PhD from the University of Tokyo in 2017. advised by Professor Taiko Igarashi. His research fields are mainly computer graphics and human-computer interaction. In particular, he is interested in enhancing various design activities by employing computational techniques such as mathematical optimization. So, Dr. Yuki, now the floor is yours.
Thank you. Can you see my slide?
Yes.
Okay, thank you. So thank you for the nice introduction. And I'm very happy to have this opportunity. And my talk is entitled as Human in the Loop Design Optimization, and which can be considered as a special form of user-driven computational design. So let me begin with a quick self-introduction. So my name is Yuki Koyama, and I'm a researcher at a Japanese National Research Institute named AIST. And my research area is the intersection between computer graphics and human-computer interaction. In this research area, I have worked on computational design and human-in-the-loop optimization and digital fabrication and so on. And here is the outline of this talk. So first, I'd like to explain the motivation of why we need to consider human-in-the-loop optimization. And then I'll talk about Bayesian optimization, which is what I have been working on recently. And then I take a deep dive talk into two recent SIGGRAPH papers, which are based on Bayesian optimization. And finally, I'll summarize the talk and give some discussion. Okay, so let me begin with the motivation for human-in-the-loop design optimization. So parametric design is the design problem where the design variation is determined by a set of parameters, and the goal is to find the best parameter configuration. And many digital content creation scenarios involve parametric design. For example, a photo color enhancement is one of the most common scenarios. So if you open Photoshop or Instagram, you see many sliders that should be adjusted carefully to make the photograph best. So, and parametric design is, of course, very important in personal fabrication context. For example, in Thingiverse, parametric models are called customizable models and shared with many end users for their personalized use. The goal of such parametric design is to find the best parameter configuration that provides the best design. And for this purpose, the designer usually has to perform many trials and errors on different parameter configurations. So this manual procedure has an analogy to mathematical optimization, where some iterative algorithm updates the search variables and finally finds the maximizer of some objective function. So this viewpoint facilitates the series of research called computational design, in which design problems are formulated as optimization problems and solved by computational techniques such as numerical optimization, machine learning, physics simulation, and so on. And I have been working on such computational design research with my colleagues. For example, I worked with Nobuyuki on computational design of freeform model airplanes, where we solved an optimization problem to maximize the flyability of the user-created airplane. And this recent work is about designing haptic force feedback by embedding magnets into fabricated objects. So in this work, we formulated an optimization problem to search for optimal magnet positions and orientations that can reproduce target haptic force feedback. And I have worked on some other projects like this. So in these projects, the design goal or the design objective was the functionality of designed objects such as flyability and haptics and so on. And similarly, many researchers in the computer graphics community have formulated various functionalities of objects and solve optimization problems. However, when considering about design goals, functionality is just one aspect of design goals. And another missing piece can be aesthetic preference. And it is natural to include the aesthetic preference as a design goal in practical scenarios. For the functionality, we can compute the goodness of a design by using predictive simulation and so on. On the other hand, for the aesthetic preference, it is very difficult to compute the goodness of a design because preference is a perceptual metric. So to handle the preference, we need to incorporate human assessment somehow into the optimization process. So about incorporating human assessment into computational systems, I'd like to mention a concept called human computation. So human computation is defined as a paradigm for utilizing human processing power to solve problems that computers cannot yet solve. So this image shows a typical configuration of human computation. The machine processor can send a query to human processors in the form of function call, and then the human processors send back data in the form of return value. So, and note that human processors can be either crowd workers from paid crowdsourcing platforms or the user himself or herself. And here is an example. The machine processor itself cannot determine which image is perceptually better. But with this framework, the machine processor can ask human processors to answer which one is preferable. In this way, the machine processor can input human assessment in its computation. And when taking this approach, we need to care about some points. So the first point is about the query design for human processors. And generally speaking, absolute assessment or absolute scoring should be avoided since the user cannot reliably answer the value. For example, given a single photograph, asking the human to provide a single score is not reasonable because, for example, there is no baseline and so on. Instead, we can use relative assessment. The user can stably answer which option is better among two or possibly more options. For example, if there are options A and B, then and the user chooses A, in that case, we can obtain relative information that the objective value for A is larger than B. So this is the first consideration that we need to care about. And the second consideration is the number of queries. So when having human in the loop, the number of total queries should be sufficiently small. For example, not like 1,000. So this is because human evaluators are prohibitively slow compared to typical optimization settings using machine processors. And another reason is that human processors can simply get tired. So taking these 2 points into account, so in this talk, I'd like to introduce preferential Bayesian optimization, or PBO in short, as a promising technique in this setup. So PBO is an extension of Bayesian optimization, or BO in short, but tailored for human-in-the-loop settings. And the benefits of PBO is that, so first, PBO can proceed with the optimization steps using relative assessment queries, unlike typical optimization algorithms. And second, PBO can find a good solution with only a small number of queries. Okay, so before explaining a preferential Bayesian optimization, I'd like to explain what Bayesian optimization is. So suppose that we have an optimization function f, which is like this image, but we don't know the analytic formulation explicitly. And what we can do is to provide some x and then observe the value fx. The goal is to find the maximizer of this function by solving the maximization problem. This is called a black box optimization problem, and we cannot observe the gradient, and the function can have multiple local maxima. The challenge here is how we should sample points strategically. So one naive strategy is to randomly sample many points, like 10,000 points, and then take the point that provided the largest value. Of course, this is not very bad for one-dimensional problems. However, when the problem is multi-dimensional, then this approach is not feasible since the search space becomes too large. So let's consider to minimize the number of necessary sampling points. So Bayesian optimization is a powerful choice for this kind of problem. So BO is a global black box optimization algorithm, and it can find optimal solutions with only a small number of function evaluations. So this property makes it useful to manage expensive to evaluate functions, objective functions. For example, it is used for hyperparameter tuning for deep learning models. And recently it was used for fabrication in the loop design problems. To intelligently sample points, BO uses acquisition functions. So an acquisition function is a function that evaluates how effective a given point is if it is sampled in the next iteration. And the point that maximizes the acquisition function will be sampled in the next iteration. So acquisition functions are designed to balance exploration and exploitation. Exploration means that it prioritizes the region with large uncertainty, and exploitation means that it prioritizes the region with high predicted value. For example, in this right image, the acquisition function, the value is large, around 0.25 or so, because the uncertainty and the predicted value are both large, around 0.25. So let me explain its behavior step by step. Okay, so suppose that this is the unknown objective function. And for the first iteration, we choose an arbitrary point since there is no data yet. Then BO tries to estimate the landscape of the unknown objective function using the observed data. at this moment, only 1 point. And for this estimation, the technique called Gaussian process regression is the popular choice. Using the estimated function, BO calculates the acquisition function, and then it finds the maximizer of the acquisition function. In this case, the farthest point is chosen. Then BO observes the function value of the chosen point. Using the available observed data, BO updates the estimated function and the acquisition function as well. Then again, it finds the maximizer of the acquisition function and then observes the data points like this. So this procedure is repeated several times. And at this moment, the acquisition function considers it is worth sampling around the current maximum, which is the red point. And this reflects the exploitation aspect of the acquisition function. And then the next iteration looks like this. So the shape of acquisition function changed. And now this acquisition function considers it is worth sampling around this region, this unvisited region. So even though the predicted value is not very high, the uncertainty is also very large. So it prefers exploration of this unvisited, uncertain region. Then it becomes like this. And then finally, we could find a very nice solution with only 12 iterations in this case, which is very efficient, I think. Okay, so now let me explain preferential Bayesian optimization, or PBO. So PBO is an extension of BO, which runs with relative assessment queries instead of absolute assessment. So we can use PBO with human processors. And similar to BO, PBO can find good solutions with only a small number of preferential feedback iterations. So this property is important because human is expensive to query. Okay, so this slide shows how PBO works in a simple one-dimensional problem. So in this case, we use a pairwise comparison query in which the current best point and the maximizer of the acquisition function are compared in each iteration. So for the first iteration, we randomly sample 2 points and then compare them to determine which is higher. Then we calculate the acquisition function and determine its maximizer. And this maximizer is compared with the current maximum, like this. And then we calculate the acquisition function again, and then determine its maximizer here. And this maximizer is compared with the current maximum in the next iteration, and then updates the acquisition function like this. So this procedure is repeated several times. And in this case, we could find a very nice solution within only 8 iterations without using any absolute assessment or absolute function value, but using only relative assessment or pairwise comparison. Okay, so now I'd like to explain our work which extends PBO for more efficiency and applies it to design problems. Okay, so this work was published at SIGGRAPH 2017. And in this work, we made two specific contributions. The first contribution is the concept of crowd-powered design optimizer, or crowds in the loop design optimizer. So this optimizer solves optimization problems using crowdsourced human computation. And the second contribution is the technique called sequential line search, which is a new extension of preferential Bayesian optimization. And this shows the concept of our crowd-powered optimization solver. So suppose that there is a crowdsource button in the interface, and the user can push it when necessary. Then the tool runs the optimization process in the backend. And finally, the user can obtain the optimal slider values. This is enabled by decomposing the original high-dimensional search task into a sequence of line search microtasks. The line search task is much easier than the original problem and can be easily performed by crowd workers. And after some iterations, the system finds the optimal parameter values. This algorithm is called sequential line search. The key idea is to use a microtask design that is different from the previous work. The previous work used the pairwise comparison query, which can be the simplest relative assessment task. Instead, in this work, we ask crowd workers to perform a single slider manipulation task, which is sufficiently easy, and this is still considered as a relative assessment within this one-dimensional subspace. And this microtask design provides much richer information than pairwise comparison, and so the optimization can converge much faster. So we extend the PBO to determine the one-dimensional subspace to construct a slider for each iteration. So we call this subspace as a slider space. And we construct this slider space as follows. So first we choose the one endpoint called X plus, which represents the best point observed so far. And second, we choose the other endpoint called XEI, which is the point that maximizes the acquisition function. So note that we use the expected improvement here as an acquisition function, since it is a popular choice. Then by connecting these 2 points, we construct the one-dimensional slider space. Okay, so here is an example optimization sequence. So suppose that we want to find the maximizer of this two-dimensional unknown function. First, the system generates an initial slider space randomly because there is no information yet. And the system asks human evaluators to perform a line search task using this slider space and obtains the point called X chosen, which represents the maximizer, which represents the maximum within this one-dimensional subspace. By using this information, the system updates the internal models, and especially the system obtains the X plus, which is the current best point, and the XEI, which maximizes the acquisition function. By connecting these 2 points, the system determines the next slider space. And by using this space, the system queries line search and then obtains the X chosen. By using this observed data, the system updates the internal models again and then obtains the X plus and XEI again. By connecting these 2 points, the system determines the next slider space and then obtains the X chosen by line search. So the system iterates this process until a good solution is found. Okay, so this solver can be applied to various parametric design scenarios, including photo enhancement. Okay, so this shows the original input image, and this shows the results of the crowd-powered solver. So let's see again. So this shows the original input photographs, and this is the results. So I hope you see some improvement in the colors. So to evaluate whether this result is reasonable, so we conducted a simple experiment in which another set of crowd workers was asked to vote for the best image among several options. So this shows the result. The leftmost image is the original one, and the second one is the one produced by crowds or our method. And for comparison, we also show the results of auto enhancement in Photoshop and Lightroom. And this is another result. And overall, the crowds prefer the results generated by crowds. This result is, we consider this result is reasonable because the crowd-powered solver can produce a solution that is people's choice. So it is natural that people actually preferred them. So this demonstrates one of the advantages of having crowds in the loop of the optimization. And this solver can be used for different scenarios such as shader parameter adjustment. So since our method uses human intelligence in its loop, so we can just specify reference photographs to obtain corresponding parameters. So these are the results. The top image is the input reference photograph, and the bottom is the bottom visualizes the material obtained by the crowds in the loop optimization. So we can use this kind of fuzzy input, fuzzy specification, thanks to the human intelligence. So we evaluated this method by comparing it with baselines. So I would omit the details, but the conclusion is that our method was much faster than the other baselines, including the previous work using pairwise comparison. So in this work, we proposed a novel, efficient human-in-the-loop optimization framework that is based on PBO. And the line search task, the design of line search task was simple enough for crowdsourcing and was useful to reduce the number of necessary iterations drastically. And human-in-the-loop systems need human evaluators. And based on the types of evaluators, we can roughly classify human-in-the-loop systems into two categories. The first one is crowd-in-the-loop optimization, as seen in the previous project. And in this case, many paid crowd workers are repeatedly asked to perform perceptual microtasks. One constraint is that the task design should be sufficiently simple so that crowd workers can easily perform. The other one is user-in-the-loop optimization, in which the single user is repeatedly asked to perform perceptual assessment interactively. In this case, the task design can be a little more complex compared to the crowdsourcing setting. Now, let me explain our recent work about user-in-the-loop optimization. So this work was published at SIGGRAPH last year. And in this work, we take a user-in-the-loop approach and propose a system called Sequential Gallery. So our target is a set of design parameters, and we want to find an optimal parameter set that provides the best look. And the Sequential Gallery is an interactive optimization system that can be used for this kind of parametric design problem. And first, the system shows options to the user using a grid interface like this one, and then asks the user to choose the best option in this grid based on the user's preference. Then the system updates the options using a grid view, and again asks the user to choose the best one from the grid. This process is iteratively performed several times, and finally the user can obtain the optimal parameter set. The key point is in the query design. In the previous project shown in the center in this slide, the previous project used a slider interface to let evaluators explore a one-dimensional subspace. This was the key to reduce the number of necessary iterations compared to using the pairwise comparison query. So in this work, as shown in the right in this slide, we let evaluators explore a two-dimensional subspace. Because a 2D search query can provide much more information than a 1D search query, this makes the number of necessary iterations even smaller. An additional benefit is that this 2D search query has a good compatibility with the grid interface. Now let me explain the workflow of the system. So suppose that this is the 2D subspace that the algorithm determines. Then the system asks users to select the best one from the grid. And based on this preferential feedback data, the algorithm determines the next plane. Then again, the system asks the user to select the best one from the grid, and using all the accumulated preferential data, the algorithm determines the next search plane. Like this way, the system proceeds the iteration. We have some benefits of using this grid interface. For example, it allows the user to easily grasp or understand the available options in the current 2D subspace by just seeing the grid view. And also, since it is its interaction is WYSIWYG, the user does not need to be familiar with raw parameters. Okay, so one question would be, how can we determine the next plane in each iteration? So in each iteration, we want to select the most effective 2D subspace or search plane for the next query. And the effectiveness here is in terms of finding the optimal solution. The question is how to define the effectiveness. For this, we can use the acquisition function used in the standard Bayesian optimization. So we write the existing acquisition function used in the standard BO as a point and this takes X as input, the point as input, and then evaluates its effectiveness. Then we write the proposed plane-wise acquisition function as a plane, and this takes a plane as input and then evaluates its effectiveness. We propose to define it as a straightforward surface integral of the point-wise acquisition function. And in practice, this integral is approximately calculated by sampling. Using this definition, now we can choose the next plane by solving this maximization problem, which is easily solved by standard optimization techniques like LBFGS and so on. Okay, so now I'd like to talk about the applications, and the proposed framework can be applied to various parametric design scenarios. And this shows the result of photo enhancement controlled by 12 different parameters. So this is the user interface of the system. The task for the user is to choose the best option from the grid by clicking it. So, and as you see, the system offers zooming functionality, so zoom functionality, that is once the user clicks one of the options, the system zooms so that the user can pick up more nuanced option precisely. And after several iterations, the user can obtain the optimal parameter set that provides the best enhancement for the user. And next, we show another application on 3D body shape modeling using a pre-trained model. So here, the user needs to find a 10-dimensional vector that generates a desired shape. So suppose that the user wants to create a character from a fictional novel that is given this text description of a character. The user wants to generate a suitable body shape for this character. And after 7 iterations in this case, the user got this model from this text description. And we evaluated the performance of the proposed method. And in this experiment, we considered the 3 conditions. The first 2 are the baselines, and the last one is the proposed one. The first baseline is the sequential line search method, which is proposed in the previous project. And the second baseline is called SPS random, which is a plane search, but the plane is only randomly chosen. And here are the results using synthetic test functions. The vertical axis represents the optimality gap, so lower is better. And the horizontal axis represents the iteration count. So as the conclusion, ours consistently outperforms the baselines. Okay, so in this work, we proposed a novel user-in-the-loop Bayesian optimization algorithm combined with a tailored grid interface and demonstrated that it could efficiently solve perceptual design problems. The most important point is that this efficiency was achieved thanks to the tight integration between algorithm design and interaction design, which indicates that we need both computational viewpoint and interaction viewpoint to investigate this research direction. Okay, so now let me summarize this talk and give some discussion points. So today I talked about human-in-the-loop optimization, which can be used for solving problems with perceptual objective functions such as preference. Then I introduced preferential Bayesian optimization as a promising technique for this purpose. It can reduce the number of necessary queries, which is important because human is expensive to evaluate. And also it can use relative assessment, which is important when we ask human to perform perceptual evaluation. As we saw in the two projects, tight integration between algorithm design and interface design would be the key to achieve higher efficiency in human-in-the-loop optimization systems. So in this talk, we assumed that the objective function is defined by preference only. But in practice, especially in personal fabrication scenarios, it is very important to consider both functionality and aesthetic preference at the same time. So one of the most important next challenges is to formulate a hybrid objective function that consider both functionality and aesthetics at the same time and build a human-in-the-loop framework tailored for this situation. And another possible approach to consider both functionality and aesthetic preference is to perform some user-in-the-loop optimization within a functional subspace or functional manifold, where all the possible solutions are ensured to be sufficiently functional. By this could be done by either pre-computation or real-time simulation. And this is also an interesting future direction. And finally, most of the source codes related to this talk are available for C++ and Python users. And I'd like to thank all the collaborators. Okay, so thank you very much for listening. So that's all from me.
Okay, thank you, Yuki, for the nice talk. So currently, so I have a few questions about your talk. So the first one is that I see this Bayesian optimization is quite impressive from your introduction. So you have shown that for this 1D search, is only using 12 iterations, you can find an optimal point. My question is that how is the ability to extend this Bayesian optimization to high dimensional space? For example, if for 2D, I mean, if with more variables, how is the performance of this optimization method?
Yes, that's a very good question. And actually, Bayesian optimization is known that it is not good at high dimensional space, like more than 20 or more than 30 dimensional space. So that's the limitation of Bayesian optimization. So it is the same in preferential Bayesian optimization. And in practice, we need to perform some dimensional reduction beforehand. So that's the one approach.
Yeah, that makes sense. Okay, yeah. We have one question for Yuki from ZG1. So he asked about could you add hard constraints in your current setup, especially when the hard constraint is evaluated by using time-consuming FEM. So this, I think this should be, I think he may ask the first speaker, I mean, Nobuyuki, because he talked about this FEM. So
yes.
So maybe let me repeat the question.
Yes.
Okay. So he asked, could you add hard constraints in your current setup, especially when the hard constraints is evaluated by using time-consuming FEM?
Yeah. I think it's possible to incorporate a constraint that is discretized with some method, numerical method. yeah, we can think of various approach. Of course, we can, linearize that constraint,
Okay.
such that we can, do some linear interpolation, or we can do some linear feedback in by linearization of the constraints, or we can use some penalty method to to constrain the design space in some to satisfy approximately the constraints. Yeah, there is various approach, and it's problem dependent whether we choose some approach. Yeah, but generally, I think it's possible to incorporate some constraints.
Okay. Okay, I have one question for Nobuyuki. So
Sure.
I see a few of your example projects. So you do this interaction on the 2D space and then show a simulation in the 3D space. So it's very cool because for user interaction, 2D is more easier to control than 3D.
Right.
So so I just wondering, so in what case is possible to do this kind of interaction? I mean, you do the simulation in 3D and do interaction in 2D.
So I think the human is better understand the two-dimensional, shape
Yes.
rather than the three-dimensional shape.
Yeah.
So yeah, when design some design interface, I specifically think about kind of 2D. The design interface will be as 2D as possible.
Yes.
Yeah. Like the airplane design, like there's a cross section of the
Yes.
airplane, and I choose like top view or side view, so that the user only manipulates the shape in 2D.
Yes.
Or in case of Metalaphone, it's just a top view. Yeah. But yeah, generally like so like 3D freeform design is very difficult.
That's true.
Yeah. So, but yeah, it's a kind of choice. But if the designer, if the user want to have fully three-dimensional sculpture, I think it's very difficult. But intentionally limiting the design space to make the problem simpler, it's one of the viable approach when we think about the personal fabrication, because most of the people want some easy, like interface, and only some, very special professional want to have full three-dimensional interface. So yeah, I think the limiting the interface is very important.
Yeah, that's true. Okay, so I have one more question for both speakers. So in both of the talks, you have mentioned about this functionality and this functional design. So now we know for some kind of terminologies, it have a concrete definition. For example, if you mention about this structure stability or this, so they have a concrete definition. So then for functionality, do we have a general definition, or it's specific for the design that you want to make?
Yeah, I as far as I know, it's very specific to design.
Okay.
And yeah, there is no, I think, uniform or general, definition of the functionality.
Yeah. Then one more question is that because we can design lots of various kinds of products or objects. So can we do, for example, a classification? So then we can classify them based on the functionalities. And then the good thing of this is that once we have this classification, you have the same method that can apply to all the objects or products in this class.
Yes.
So
yes.
Because I see both of you have designed different a wide variety of these products. And for example, this cloth, this the plane, and also this I mean some instruments some instrument to play some audio. So so is there some idea in your mind about this classification?
Yeah, of course, if we know the problem, we can classify the problem and apply it. But I think that's nice future direction. But we haven't reached there yet because there's so many, like functionality definition that we have no idea how to make it interactive, to make it, put into the in the human design.
Yeah.
So I'm first, developing some, some method to tackle these problem, and then, but eventually, I think it's very nice if we can, more can develop some algorithm that handle more general problem.
Yeah, that's true.
Yeah, if it's cool that the system automatically identify the functionality.
Yes.
Like if the design say, please design a chair, and then the system figure out how the chair should be, like like in terms of stability, structure, or ergonomics, and manufacturability, or everything. Yeah, but it's it's kind of still developing field, so there's a lot of things to come.
Yeah, I agree. I think it can be a very promising research direction. Yeah, because this will bridge the gap between our design and the real product.
Mm-hmm.
Yeah, that's true. Okay. Okay, I think that's so. Currently, there's no more question from the audience, and I also don't have further questions. So, so thanks again for both speakers to join this talk, and thank you for it's really inspiring.
Thank you very much.
Okay.
Thank you.
Yeah. So I think this is the end of this seminar. Okay. See you.
Yes. See you. Thank you very much.
See you. So
Okay,
thank
bye.
you.
Okay,
Yeah.
bye-bye.
Yes. Thank you.